What we have here is a square wave going into a true integrator circuit. The line down the middle is the second channel, which right now is set to ground. I'm going to switch that on. Now the circuit is not powered up at this point, so when I switch the scope on, you're going to see an artifact of that square wave feeding through the passive components in the circuit to the output. Now when I turn the power on, you're going to see a triangle wave, and that triangle will be going down when the square wave is high and up when the square is low, because remember, the basic integrator is an inverting integrator. Now, a word of warning, because you're going to have to watch for this. I'm going to turn it on. You'll see the triangle wave, and then several seconds later you're going to see something a little bit different. Here we go. There's our triangle wave. Now watch the peak at the top. Whoa! Why did it do that? I didn't touch anything. It just did that. Alright, let's try this same thing again. I'm going to turn it back off. Let's let the capacitors and the power supplies and in our circuit discharge to zero, which takes a few seconds. The strange changes in the output result from this discharge. I'm going to switch back to ground. We've still got our square wave. Now, I'm going to turn it on again. Here we go. And this time, I'm going to turn the power back onto the circuit. But now watch what happens. Whoa, what is going on here? Why is it up? And look at that, it got to a certain point and then the top got bent out of shape. Alright, here's what's going on. The first time we did this, I had AC coupling on the scope so that it filtered out the DC component. The second time I switched it to DC so it showed the DC component. So what you see there is that after I switch it on, the DC component begins to increase. And it increased until it bumped its head on the upper power supply limit. Now there's not necessarily any reason why it would have to increase, depending on what the DC component of the input, bias currents, and the input offset voltage are. It could decrease just as easily. Right here is 0. That's 0. We're set on 5 volts per division, so that's 5, 10, 15, so it's flattening out just under 15 volts, exactly what we would expect for an operational amplifier, because it just can't quite get up there. Now, within the accuracy of this scope, it looks like we're at about 14 volts, but I'd have to double check that exact figure. Let's switch to a more sensitive scale here and shift it down so we can see it. You may also note that when the square wave switches after the output is saturated, that there is some sort of glitch in the output. This will be explained in a future video. So this is one fairly serious problem, because you saw that happened really fast. It only took a few seconds for it to drift up and bump its head on the upper power supply limit. So the DC component of the input, as well as the input bias current and the input offset voltage, can really wreak havoc on a true integrator. In our next video, we will add a single resistor to the circuit to fix this problem.